Okay, so this lesson is about writing net and complete ionic equations. In order to get the most out of this lesson, you first need to know about balancing equations, you need to know about classifying equations, you need to know about predicting the products of equations. The only kind of equations for which, at least at this point in time in our class, for which complete net ionic equations are written are the single and double replacement reactions. So, for example, one of the reactions you did in this lab was a reaction in which you placed zinc metal in hydrochloric acid. Or you put the zinc in first and then put hydrochloric acid on top of it. But essentially you're putting in hydrochloric acid. Okay, so the zinc is actually in the water with the acid. Austin. I understand, but that's not why I called your name. It's actually submerged in the water, but until the reaction actually starts, it's initially a solid. Okay, so we're starting with a solid zinc. We're starting with the acid dissolved in water, and so we call it aqueous. Now you observed, I hope everybody did, observe there was a reaction here. Did you? Okay. And what was the reaction appear? How did you notice? What evidence did you have there was a reaction? What observation did you have that would have supported the claim that there was a reaction? So if the zinc is displacing the hydrogen, then according to what we were talking about yesterday, you should have gotten hydrogen gas. Okay. And since the zinc is displacing the hydrogen gas, it must be joining up with the chlorine. And you have to be able to balance formulas. Zinc has a 2+ charge, chlorine has a 1- charge, so we need 2 chlorines to balance this formula. And since what you saw, if you were carefully paying attention, were bubbles, you probably also saw that whatever else was in there sort of disintegrated. Okay? Which, what was happening is this is actually dissolving in the water. So if you look at your solubility rules, you should be able to figure out that zinc chloride is supposed to be soluble. And so you saw evidence that that was the case. Chlorines are, as are bromines and iodines, are soluble with the exception of when they're bonded to a few things. Okay? Alright, so this is the initial reaction. What I haven't done yet is to balance this equation. Let's do that. Make sure we've got it right. So I've got 1 zinc over here, 1 hydrogen, 1 chlorine. Over here on this side, I've got 2 hydrogens, 1 zinc, and 2 chlorines. So I need to balance the equation so the number of atoms are the same on both sides. And to do that, I'll put a coefficient here, and that's going to change the number of hydrogens to 2 and the chlorides to 2, or the chlorines to 2. Okay? So now the equation is balanced. What we're going to do now, that we have this balanced equation, is I'm going to introduce you to the complete ionic equation. Now, anytime you dissolve an acid or an ionic compound in water, it dissolves because the ions actually break up. If you recall, when we were first balancing formulas, we tried to figure out how many hydrogens we needed for every chlorine. And so we looked up the charge or oxidation number of the hydrogen. We figured out or looked up the charge on the chloride, and we found that this was a plus charge and this was a 1- charge. And that's how we got a 1-to-1 ratio here. And over here, we just talked about this a moment ago. The zinc had a 2+ charge, and the chlorine had a 1- charge. Well, these ionic compounds are actually ionic particles. They're charged particles, and those separate in the water. So we talked about this in the last unit, that these are actually charged particles, and they're strongly attracted to water molecules, because water molecules are highly polar. So Polar things are attracted to water molecules, and as are charged particles, that is to say ions, they're also attracted to water because of the polarity of the water. Okay? And so when they actually dissolve, they dissolve by breaking up into separate ions. So in reality, once you put hydrochloric acid or hydrogen chloride in water, it's not really HCl anymore. It's H plus and Cl negative that is dissolved and floating around in the water. Okay? What we're going to do with complete and net ionic equations is to show what we're really getting in that solution. Okay? Well, the same is true for this salt over here, this ionic compound. When it's dissolved in water, it dissolves because the zinc ions separate from the chloride ions, and those are taken up in the water molecules. Okay? And so what we're going to do is to write this double replacement reaction, this complete ionic equation to show that. So the zinc is a metal. It's not broken up. It stays the same. It was a solid. Okay? But the hydrochloric acid, because it's a set of charged particles, acids behave like ionic compounds even when we're naming them. Remember, we named them first like an ionic compound and then like an acid? Okay? When acids dissolve in water, they behave like an ionic compound. So this breaks up into separate charged particles, H plus and Cl negative. But how many H pluses or hydrogen ions or protons do we actually have here? 2 of them. Okay? So while it was 1 H and 1 Cl to balance the formula, in this complete ionic equation, we actually have 2 hydrogen ions because we have 2 HCl's. Okay? How many chlorides do we have? 2. And we said it dissolves by breaking up, so it's true to say that this is aqueous, but it's also true that these are aqueous as well because they became dissolved in water because they broke up. So this is a kind of chemical equation that more closely reflects what is really going on in that water solution. Okay? Then, on the other side of the equation, you had hydrogen gas bubble out. Well, that wasn't dissolved in water because it was bubbling out. It was evolving out of the solution. Okay? You get precipitation, that stuff is settling to the bottom. You get an evolution when things come out the top. Okay? So this was evolving out. And so it's H2 and it's a gas. It's not part of what's being dissolved in the solution, at least dissolved in terms of actually breaking up. Only salts, which is to say ionic compounds, that are soluble, and acids, which are soluble, will break up. That's the way they do it. So we're going to break this up too, because we said it does break up. It's an ionic compound. It's soluble. It's one of your solubility rules that chlorides are soluble, except when they're bonded to a few things. So the zinc ions are going to be in the water, and zinc is a 2 plus charge. They're going to be separated from the chlorides in the water. And the chlorines, or chlorides, are dissolved in the water. And how many chlorides do I have? 2 because of that 2 there. All right. So this is a complete ionic equation now. And that's the process you go through to figure it out. To write a net ionic equation, we're going to eliminate any ions that are exactly the same on both sides. We're going to eliminate any ions that are exactly the same on both sides. So to figure this out, you've got to be really careful to get this complete ionic equation right the first time. Because if your complete ionic equation isn't right, then your net ionic equation may be also wrong. Okay? Does that make sense? So, zinc over here, this is a metal. It's a solid. And by the way, if you didn't know this, let me make sure I'm really clear about this. Any elements that are by themselves or are only bonded to themselves have a 0 oxidation number. So this is an oxidation number. In an ion or the particles that come apart in an acid, these charges are also the oxidation numbers. Okay? Oxidation numbers become charges when you have an ionic particle. When you have an element that's by itself or only bonded to itself, the charge on this is 0. Okay, so there's no charge on this. So it remains like this. Okay, it's a solid, it's not dissolved in water, and there's no charge on it. Okay? So here's a hydrogen ion. Is there also a hydrogen ion on the right-hand side of the equation? Okay? The correct answer is no, and here's why. Because this isn't an ion anymore. This over here is an element bonded to itself, and that has a 0 charge. Okay? Got that? So this is a charged particle, this is not. This is aqueous, that's not. This is H2, this is 2H+. plus. Two different things. So these are going to be kept. And this zinc over here that's a solid is not the same as this zinc. This is a solid, that's aqueous. This has no charge, that has a charge. Two different things that we're going to keep both of those. Alright? 2 chloride ions, aqueous. 2 chloride ions, aqueous. We don't keep those. Okay? So what happens in this reaction, in reality, is that the chloride ions stay chloride ions. They basically don't do anything. Right? They're the same on this side as on that side. They haven't done anything. You see what I'm saying? These are called spectator ions because they're sitting on the sidelines. Okay? These are called spectator ions because they're sitting around doing nothing, kicking up their feet, drinking a Coke, eating a hot dog, but they're not doing anything. Got it? That's what spectators do, right? Sit in the stands, drink a Coke, eat a hot dog, whatever. All right. Y'all don't seem to find my jokes very funny today, but okay. I got it. I know they're not very good. That's all right. Huh? I know it, but I'm just trying to get you to sort of visualize what's going on, okay? I'm trying to get you to transfer those things I'm saying from short-term memory to long-term memory by connecting the things that you already know. Got it? All right. So this is a net ionic equation. Say what? No, you could actually bunch it up together. So you don't have to have this separated from that. It's probably better if I put it together, but I'm just showing you how we leave out the things that are exactly the same. So again, it's really important that you get the complete ionic equation right before you write the net ionic equation. If you don't have your complete ionic equation right, the net ionic equation is probably also going to be wrong. Okay? Got to be careful. Got that? All right. So we just did a lab in which you ran a number of these single replacement reactions. Okay? And as homework, you're going to pick 2 for which there are reactions. Okay? For which you have evidence to support the claim that there was a reaction. And you're going to write complete ionic equations and net ionic equations for those 2 that you choose. Any 2 you want. Okay? Got that? So we did this example for single replacement reactions. You're going to practice a couple at home. And the time remaining, let's look at a couple of, or at least one, double replacement reaction. Okay? We'll give you a double replacement reaction. You're supposed to be able to predict the products. So I'm just going to give you the reactants. Okay? You're going to predict the products if there's a reaction. And if there is a reaction, you're going to finish the equation by balancing it to do the physical states, that sort of thing, all that's required, and then write complete and net ionic equations for this equation. So your assignment is to determine if there's a reaction. If there is a reaction, write balance products over here, then balance the equation, making sure you include your physical states, and then write complete and net ionic equations for them if there is a reaction. It's all about if, okay? If there's no reaction, you just write NR, you stop. There is no complete or net ionic equation if there's no equation, period. That makes sense? If there's no driving force, there's no anything else. You just stop. Got it? Alright, for time we'll kind of rush through this, alright? So the silver is going to join up with the chlorine. So we get AgCl. And chlorides are mostly soluble, but not when they're bonded with silver, so this is a solid. I need to balance the formula. Silver has a 1+ charge, chlorine a 1 negative, so that is balanced. Calcium is going to join up with the nitrate. All nitrate compounds are aqueous, so we're going to list this as aqueous. Calcium has a 2+ charge. Nitrate has a 1 negative charge. So to balance this formula, I need a 2 after the nitrate to have 2 nitrates balancing out the 2+ on the calcium. Now I need to balance the equation. And because we're running short on time, I want to just balance this by inspection instead of using an atom inventory. Remember, you're required to use an atom inventory, correct? But I'm going to do it for speed. Just put a 2 here and a 2 here to balance the equation, okay? In the complete ionic equation, anything that's aqueous and ionic, or aqueous and acidic, will be split up. Nothing else can split up, okay? So this is aqueous and ionic, so I split it up. I'll have 2 silvers, and that's aqueous because the compound it came from is aqueous. 2 nitrates, because the compound it came from was aqueous. It's going to be here. I'll have 2 in front of it. In front of this thing means I have 2 of everything. I've got 1 calcium. Excuse me. Wow. I hate that when it happens. Alright, calcium 2+ aqueous. 2 chlorides. Over here, this is a solid, so we don't do anything with that. We leave it just the way it is. We've got a calcium ion because this is an ionic compound. It's aqueous. And 2 nitrates. They're aqueous. Alright? So the silver changes. We're going to keep the silver in the net ionic equation. This is the complete ionic equation. Now we're writing the net. The silver changes. The nitrate stays the same. We're not going to write it. The calcium stays the same. We're not going to write it. The chloride is an ion here, but it's a solid in this silver chloride over here, so we're going to keep the silver or the chloride. And the only thing we have on the other side is the 2 silver chlorides. And there's your net ionic equation.